Hello there, welcome. Thank you all for joining me today to discuss high performance application, API, and microservice security testing. Today's webinar is hosted by GigaOm and sponsored by NGINX. I'm Jake Dolezal, and I'm a technical lead on a team that conducts performance testing at GigaOm. I've been doing application and database performance testing for over 6 years. Everything from the TPCH and TPCDS on the database side to JMeter and load testing on the application API web side. I am also a consultant and work with clients on data and application architecture and implementations for both operational and analytical sides of the house. In today's webinar, I will be discussing the demand for high-performance application security, from its challenges and business requirements to how it must fit within the existing ecosystem and still be able to do its job, that is, to secure and protect applications. We will be discussing the landscape of a few available cloud-based web application firewall solutions, more specifically, NGINX App Protect, mod security running on NGINX, Amazon Web Services Web Application Firewall, and Azure's WAF platform. Third, I will go over how the testing was conducted, the methodology we used, and even show you how you can repeat these tests on your own. And of course, I will reveal the results of our performance testing and see what that did to all of our platforms. At the end, we will have a brief question and answer period. During the course of the webinar, you may submit questions to our moderator, who will then pass them on to me. I'll do my best to answer these as time permits. Data, web, and application security has evolved dramatically over the past few years. Just as new threats abound, the architecture of our applications, how we build them and how we deploy them, has changed dramatically. We've traded these monolithic applications for microservices now running in containers and communicating via APIs. All of this we're now deploying through automated continuous integration and continuous deployment CI/CD pipelines. The frameworks we have established to build and deploy applications are optimized for our time to market, time to value. Yet, security remains of utmost importance. The challenge of securing and innovating is profound these days. You really need a lightweight but integrated security solution that won't impede performance and delivery. You do not want a bottleneck at your security solution. DevOps teams need security controls that will work across all our distributed environments, but without invasively slowing down or burdening the release cycle or performance. The maturation of these controls and processes ultimately transitions into a realm we call DevSecOps, where security is built right in to the CI/CD pipeline. The multitude of deployed apps and APIs and microservices we have produce a constant flow of communication and data among applications, and it needs active management, both internal and external. Apps themselves vary greatly in their protocols, their allowed methods, their authorization and authentication schemes, and usage patterns. Perhaps, though, most important, IT departments need granular control over the entire application ecosystem to prevent security breaches and attacks, whether it's man in the middle, distributed denial of service, script, code, SQL injections, whatever the case may be. While security is of utmost importance, the pace of modern business demands high performance, and this is especially true in our application and microservice enabled enterprises. The conventional approach, still effective today, of deploying a perimeter web application firewall for filtering and monitoring traffic between our apps and the internet, while very still effective, is not quite enough. Even internal communication between apps and microservices on the trusted corporate network can be compromised and must be addressed. We recommend a defense in-depth strategy with multiple WAFs. In our study, we focus on web application security mechanisms that are deployed in the cloud, close to applications, because the cloud enables enterprises to differentiate and innovate with microservices at a rapid pace. We can have microservice endpoints be cloned and scaled in a matter of minutes. The cloud offers us elastic scalability compared to on-premises deployments. It enables faster server deployment and application development and less costly compute. Well, most of the time. Sometimes that's not necessarily true. However, the cloud can be just as vulnerable, if not more so, to attacks, breaches, and as on-premise APIs and apps are. However, for many organizations, performance is still a big deal. They need to ensure secure transactions at rates that keep pace with the speed of their business. A WAF or application security solution cannot be a performance bottleneck. Many of these companies seek a solution that can load balance across redundant microservices and enable high transaction volumes. The study that I'm going to show you today is specifically about securing apps and APIs and microservices tuned for high performance and availability. And by high performance, we mean companies that experience workloads of more than 1,000 transactions per second and require a maximum latency of 30 milliseconds across the board. So furthermore, in terms of high performance, we are focused particularly on latency. And latency at the 99th percentile and above. Now you're thinking, why do I care about the 99th percentile? It seems like such an outlier case. However, in our experience, these measures are extremely important to latency benchmarking results because it tends to be, you see these things multimodal over time, with tops of the spikes representing hiccups in response time. These hiccups do matter. Think about it. If the median response time or latency is less than 30 milliseconds most of the time, but you have hiccups above, say, 1 second, the cumulative effect will impact subsequent user experience. The real life example I can think of is if I go to a fast food drive-through where the median wait time is only 1 minute to get my food, I think, you know, that's really good. That's good customer service. I can get in and out in my food in just a minute. But however, what if the customer in front of you has a problem with their order and it takes 10 minutes or more to resolve? Guess what? Your wait time is now 11 minutes because your request came in line after the hiccup. That 99th percentile event delay becomes your delay. And these numbers can add up. If you're a business and you're experiencing 1,000 transactions per second, that translates to 3 billion API calls in a single month. And it's not uncommon for large enterprises with high-end traffic levels to experience 10 billion or more in that same 30-day period. Make no mistake, performance is a critical factor when choosing an API security solution. You don't want a bottleneck. As I previously mentioned, we reviewed and tested 4 different cloud-based solutions. Now, you're saying NGINX doesn't have to be in the cloud. Absolutely true. You could deploy this on-premise just fine. Now, obviously, the other 2, AWS and Azure, are cloud only. So I just wanted to preface that when I say cloud-based solutions. So cloud, hybrid, on-premise, NGINX is good to go. Now, with NGINX App Protect WAF, Mod Security, or ModSec, AWS WAF, and Azure WAF. Let's talk about those a little bit. We all know NGINX. It was first released back in 2004 as a reverse proxy load balancer, web server, mail proxy, HTTP cache. You all know this. It was offered free to use open source software. Its popularity is really evident today, and I checked a Netcraft report back sometime last year, and it said that 37% of all public websites use NGINX, compared to 24% of the Apache web server. Now, if you would have done that same study 10 years ago, you would have seen that Apache was 70% of all public websites. So it really shows how NGINX has dominated in this area. You may have also heard that NGINX was acquired by F5 Networks in 2019. That's a big deal, and I'll tell you why in just a second. NGINX Plus is a commercial offering built on top of the NGINX open source platform. It was first introduced in 2013 and is now a robust load balancer, Kubernetes ingress controller, API gateway, sidecar proxy solution, and many more. It's deployed millions of instances worldwide. The NGINX App Protect, which is what we're testing, combines F5's advanced WAF technology with NGINX's native agility and performance, making it a truly natively run right there with NGINX Plus. So for configuration purposes, we installed the latest version of attack signatures and threat campaigns to enable the highest level of protection during our testing. Now, mod security, or ModSec, has also been around for a really long time. It was first developed and produced in 2002. It was, of course, made for the Apache web server. In 2010, it was acquired by Trustwave Spider Labs and released as an open source cross-platform WAF module. I've heard it called the Swiss Army knife of WAFs. It's still a great tool. It enables web application defenders to gain visibility over all their HTTP and HTTPS traffic, has a rules language that is really commonly known, and you can use it to implement advanced protections. For our test, we employed the OWASP Mod Security Core Rule Set, or CRS. CRS is a generic attack detection rule, covers probably 99% of security scenarios that we see, and it's a rule set that aims to protect APIs, but it includes that OWASP top 10. And it's a really good job at only having a minimum of false positive alerts. On the cloud only side, AWS's web application firewall is a fully managed cloud service. It's platform as a service. They provide a web application firewall to protect mostly AWS applications against the common web exploits that we commonly see that affect availability, security, consume excessive resources, or whatever. In our testing of AWS WAF, we installed the AWS Managed Rules Common Rule Set, kind of a mouthful, but that is basically AWS's OWASP implementation of the core rule set. On the Azure side, same story, just different cloud provider. It's also fully managed cloud service, kind of really very similar. We installed the Azure OWASP 3.1 policy. There may be a newer version of that out, but when we did our testing, it was 3.1. Now let's talk about the architecture of the testing itself. We used a simple workload to attack both the API directly for some baseline testing, or the WAF endpoint, which was serving as a reverse proxy, with a barrage of identical GET requests at a constant number of requests per second. So to perform the attacks, we used the HTTP load testing tool, Vegeta. It's free to use. It's a workload test kit available on GitHub. The Vegeta tool returns a results bin file that contains the latencies and status codes of every single request during an attack run. The attacker measures latency as an elapsed time between obviously the time it sends the request to the time that it gets it back. So if we tested 1,000 requests per second for 60 seconds, which we did, the attack tool would then record 60,000 latency values. And we use that data to compile and interpret the results that I'll share with you in just a few moments. The test also required obviously a backend API, which can listen and respond to requests. In this case, our backend API just listened for GET requests and responded with a string of 1024 pseudo-random Unicode characters, basically giving us a payload size of 1 kilobyte. What we did then is we completed 3 attempts of each test on each platform, configuration and request rate. So for example, we would start with 1,000 requests per second, run that for 60 seconds. Then we would bump that up to 2,000, 3,000, 5,000 requests per second, which is pretty high volume. After 60 seconds, we would capture those latency values at the 50th, 90th, 95th, 99th, 99.9, and 99.99 percentiles. We call those the nines. And we'd also grab the maximum latency, so whatever the slowest response time was. We recorded each of these and took the lowest maximum latency or the highest success rate in the event of errors. When I mean errors, I mean an error status code that comes back as an HTTP status code. You'll recognize these as 429s, too many requests, we know it's overloaded, or any of the 500 codes, most often the 500 internal server error. So a success rate of 100% means all requests return 200 OK status codes. So during the test, if we got any errors, we sort of reported that as a bad run. In addition to just the standard good, expected traffic, just regular API requests, we also tested the configuration ability to block bad or efficacy in blocking bad traffic. And by bad traffic, I mean script injections. So we created some script injections that would happen. So during the test runs after our baseline results, we would introduce 5 or 10% bad traffic. So as if it was getting hammered with these script injections. So it had to handle those and block those, but also allow all the good traffic without missing a beat. So for the installation of test components, for example, on the AWS side, which included the NGINX and the NGINX ModSec tests, we used AWS EC2 instances. We also used the C5N family of EC2 because of its enhanced networking capabilities. If you look it up on Amazon, C5Ns are ideal for high compute applications, including network appliances such as firewalls and routers that can take advantage of improved network throughput and packet rate performance. C5N instances offer up to 100 gigabits per second of network bandwidth and increased memory over comparable C5 instances. So basically better network throughput, which is very important to what we were wanting to do. Now, we use a different VM on the Azure side. Obviously, we wanted to create close network proximity. Now, that's a good point here. I'll go ahead and introduce, and you'll see this in the results. But we have no way with the platforms as a service to be able to guarantee close network proximity. We can get in the same region or availability zone, but that's about as good as we can get. It's one of the problems with benchmarking platforms as a service in the cloud. After we installed our software, we did make one operating system change. We increased the user limits for soft and hard open files to 64K. First, the reason why you do this is because if you're testing these high volumes of transactions, all of these represent maybe an open file. And if you run out of those, it crashes. So it's a good thing to increase that. Let's see, what else is important for you to know? Yeah, so on the AWS and Azure WAF, I mean, we're very limited on the configurations, the way we can test those. We don't know the quote unquote instance type of the AWS WAF or Azure WAF. We don't, it's fully managed, so we don't know what its CPU and memory capabilities are like. So it's very difficult to understand what that looks like. It's hard to create in cloud testing a hard or a sterile lab environment, as we like to call it. However, for full transparency and for your convenience, we have published all the configurations we used and the exact setup steps in a public GitHub repository. You can see the link down here. I'm willing to jot that down if you'd like. I'll show you what it looks like really quickly. Yeah, so it looks like this, and we've created a really nice, or I did, a README that walks you through every step of each of the components of our test. You are welcome to clone this repository, use it to duplicate what we've done, or modify it to create your own kind of test. But it's really helpful, I think, for the installation purpose. If there's time at the end, we may go through this in a little bit greater detail, but you are welcome to try it for yourself. All right, let's get to the results. Well, wait a minute. Before we get to the results, I need to do our standard fine print here. Now, I must put a disclaimer out there. Testing hardware and software in the cloud is very challenging. Configurations may favor one vendor over another in feature availability, virtual machine processor generations, memory amounts, storage configurations, for the I/O, the IOPS, input/output, network latencies, software and operating system versions, and the workload itself. Even more challenging is testing fully managed as a service offerings where the underlying configurations like processing power, CPU, memory, networking, and the like are unknown. Our testing demonstrates just a narrow slice of potential configuration and workloads. We leave the issue of fairness to you to determine, and we strongly encourage you to look past all the marketing messages and discern for yourself what of this is of value to you. We hope this study, though, is informative and helpful in uncovering some of the challenges and nuances of security architecture selection. So sorry I had to read all that to you, but it's probably important that we put that asterisk out there as we get into the results. Finally, the results. When we did our testing, you are going to see a series here of what we call latency curves. Now, usually they're a little, if you see a latency curve, it looks a little bit more logarithmic. Okay, it'll start low at the bottom or at the bottom left, and then it will curve upward, which is kind of true, but again, these are sampled percentiles and not a graduated scale across the x-axis. So they do look a little funky. I mean, but that's okay. It still gives us the values that we're looking for. And again, we're focused on 99, 99.9, and 99.99 because the base latency at the 50th or the median latency, is important to know, which is, where most the average requests will take that long, but it's those upper limits that really start to concern us. Now, I will say this. The first thing we did right out of the gate was to actually just test the latency between the Vegeta attack node and the backend API itself. The reason we did this is because we wanted to know sort of what do you call that? On a scale, a tear. Yes. So it's like if you go to, you're going to measure, take the weight of something at the grocery store or whatever, you need a tear. So you need to know exactly what the zero is. This is kind of like that because I need to know what the latency is without the security WAF in the way. And since we installed everything especially for the NGINX testing all within the same sort of cluster group of, so we tried to co-locate as closely as we could to cut down on anything. We got really fast latency. So we're talking microsecond latencies here. So if you look at the very bottom of the graph here, where it starts at 0.286, 0.311, that's 286 microseconds or 0.286 milliseconds, however you want to look at it. That's really our baseline. That's the latency if we have nothing at all. So it's pretty fast. I mean, that's really fast. When we introduced, so the next line up is the green line. That's your NGINX App Protect WAF results. As you can see, the difference between having nothing at all and introducing App Protect WAF with all the threat signatures and all the checking it does, introduced very little latency, maybe 50% more at the maximum or 99.99th percentile. That's pretty good. Mod security, on the other hand, at 1,000 requests per second was a little bit higher. So the rules engine and the rule checking does introduce some latency. Again, these things are running side by side. So it's really just it's good to plug and play these because you can really see the side by side differences of them. Now, the mod security rules, again, it's a solid tool. I'm not disparaging it. It is a good one. However, it does introduce more latency at 1,000 requests per second. Now, the good news is both of these returned 100% success rate. So we didn't have any 500 errors or 429s or anything like that. They all did perform very well. So what we did then, again, and all the traffic here is 100% good. So there's no script injections going on. This is just day in, day out traffic, all systems go, all green. Okay, so if I turn the knob up a little bit to 2,000, that's where things start to get a little interesting. Okay, so again, we tested the baseline. Here's that little light blue line at the bottom, 0.5 at the 50th, all the way to a maximum of 1.3 milliseconds. Okay, same test on App Protect WAF. Wow, not very much more. In fact, it looks like only about like, what is that, 30, 25%, 30% more. That's pretty good. Now, mod security, on the other hand, that's where we started to have some problems because now we're talking, we had some failed, we had first of all, at the 50th, it was already over a second. And that's a problem, okay? So that's not what we wanted to see. And also at the top end, we had some that just never came back. We got a few errors. So this was not 100% success rate on ModSec. So at 2,000 requests per second, which is a lot, it's 6 billion a month, that's quite a few, it just didn't handle. Now, again, we probably could have, increased the EC2 instance size in order to, maybe get some more CPU bound here. However, that costs twice as much money. So why would we want to do that? All right, so keep that in mind as we move forward. Now, so basically, we dropped off ModSec at this point because if it can't give us 100% success rate, we're done with it. So now we're up to 3,000 requests per second, and we're really just down to comparing no security at all versus App Protect WAF. And again, it's still holding very much just right there with it. So feel really good about what we're seeing here. And then at 5,000, okay, we're still doing really well, maybe 60, 75%, a little slower, but hey, that's really good. Okay, so then the next step is then that's our all good traffic, high, basically we're testing throughput at this point. How high can we get throughput? And we'll get to the max throughput results at the very end, but just for your purposes, we're just studying what's going on at these different levels. Because you can hopefully, if you're in this high performance level, you can see where, you know what your traffic is and where you would fit in. Okay, so now we're gonna back it up a little bit. We're gonna go back to 500 requests per second, but we're gonna introduce 5% of the traffic is our script injections. So this is stuff we want to reject, stuff we wanna stop. And of course, the good thing is it, obviously, this takes out the scenario of the baseline, no security at all. That's why you don't see that line on here, because obviously if we don't have a WAF in the way, then the script injection just goes right through, and that's a bad thing anyway. So that's why there's no baseline testing here. This is just a comparison. So at the 500 request rate, we're kind of back to where we were before with that. Both of these successfully rejected the requests. It just that App Protect did it about 3 or 4 times faster. So that's really cool. And this is the okay, okay? And then if you look at a little bit deeper, if you wanted to look at both, split it up a little bit, you can see the results of, on the left, this is the good traffic latency result. On the right is the bad traffic. So the bad traffic still gets rejected, so the latency gets measured there too. And as you can kind of see, in certain cases it's it just varies a little bit, but it's good to see both. Also, you've got the scenario where we have 90% of the traffic is good, so we've increased the attack of bad traffic. So we've got 10% of the requests are script injections, and you can kind of see the difference. Again, on the left, this is all of the good traffic latencies. On the right is bad traffic. All right, now we're going to compare the two cloud-only solutions, Azure and AWS, to App Protect. We kind of know what App Protect looks like against just its cousin ModSec. We want to see what it does. Now, again, I want to give you a disclaimer here. First and foremost, again, I can't assure this is not great bench. This is not apples to apples. I'll just say it. But, however, that's not the point. The point is not to create an apples to apples scenario. The point is to show you that if you have on-prem apps, if you have Azure, maybe you're using Azure App Service or AWS, you've got stuff deployed on EC2 instances, maybe you've got a Kubernetes cluster in AWS or something like that, you're going to have experienced these types of latencies. And the reason is I think it's mostly network proximity. However, but that's the best you can do. If I have a more on-prem environment, or I have everything's controlled with EC2, or if I've got, I'm using App Protect WAF, I'm going to get better latency just across the board, just because of the fact I'm using that solution as opposed to the cloud providers, because I can get that network better, not only better network proximity, but probably it's faster, as we saw it against ModSec, which Azure and AWS's implementation is pretty much a ModSec implementation. It's OWASP all over again. It probably has its own thing going on, but again, you can kind of see the difference here. And on the Azure side, we were quite disappointed with half a second at 1,000 requests per second. So our 99th percentile, we're over already half a second on response times. AWS did better. And again, now on the Azure side, we were using Azure VMs. We weren't trying to go cross cloud, okay? So if you think, oh, well, you may have, because you were going from AWS to Azure. No, we were all in Azure when we were running these tests. So we just installed a different environment and in the same availability zone. So we felt we did the best we could. Let's just put it that way. With the AWS on their side, again, you're in the 92, which is already, in my opinion, I think 30 milliseconds is sort of a hard line. If you need high performance, you need to have 100% of your traffic coming with 30 millisecond or less. So we're already above that. So, but at lower levels, it's pretty good. At 2000, if you turn that up, again, we see the issues start to compound. This is where latency starts to add on to latency. And you see that compounding effect that we talked about with the drive-through fast food restaurant scenario. Now, what you'll see here is at Azure, we're a second and a half for our 99.99 and our maximum. AWS, we're at 200 plus milliseconds, but with App Protect, we're still below 2 seconds, which is, 2 milliseconds, excuse me. Still good, really good. 3000, we dropped, Azure started to give us some, at 3000, we didn't get 100% success rate. We started to get some errors. So we dropped it off because it's hard to compare the results at that point. And as you can see, AWS, we started to near that half a millisecond on response rate. And then at 5000, we're now over a second on AWS WAF, which I've done this testing for several years now, the same exact testing, and AWS WAF has improved. I will give them that. they have definitely improved. They were more like Azure was about a year ago. So they're a little bit ahead. Again, I can't guarantee that because I don't have full control over the testing environment since it's as a service. I'm just doing a representative test so that you get a sense of what you might experience if you deployed into and used AWS's WAF platform. So now we're to the where we have the good versus the bad, where you have 95% of our 500 requests, or 475 of them, are normal, and 5% or 25 of them per second are script injections. And again, pretty similar results, a little bit, you know, some interesting. I don't think there's anything overly interesting or overly telling about these, but it kind of, what's interesting is you're actually did a little better than could have been the test. I don't know, but it did a little bit better than AWS did. So at the higher percentiles, which was nice to see. Not for just because, well, I'm not a fan of either one necessarily. I like both, but it's just interesting to see these results. With AWS and Azure, again, kind of the similar thing when you go to the 90% good and the 10% bad, where we've increased the number of script injections per second. And then last, this graph, which this can be a little hard to read, but it really shows you what maximum throughput. Now this is where, okay, this is where we just basically repeated the test and we just kept amping up the request rate until we got errors. So the big, I don't like the order of this chart. It's kind of weird, but I didn't draw it, so that's okay. But the black bar in the middle, the no security one, that is basically your baseline. So at 37,000-ish requests per second, it was after that point that it just broke down. I mean, and I mean, granted, that's a heavy load, attack load. Okay, now if you go down, look at this. App Protect, it didn't start to give errors of any kind until we got to about 19,000. That's good. That's really good. So we didn't even see any errors until we got that high. And then the others with ModSec, again, you saw the results earlier. We started after 2,000, we started to see problems. So for high performance, ModSec didn't hang on that, you know, we didn't get those 100% success rate that we need. So maybe you've got some SLAs that you've got to meet. That's something to keep in mind. For on the cloud side, the AWS did pretty good. It held on until about 6,000 and then started to throw errors. And then on the Azure side, it was closer to what we saw. Again, you saw the results earlier with ModSec. So in summary, for everything that we've seen so far, what we found was that this particular test on this day, using this particular workload, is that enough fine print for you? Using these particular configurations, the API requests came back with the lowest latencies and the highest throughput on NGINX App Protect, hands down, compared to all the other 3 security configurations that we tested. NGINX App Protect WAF outperformed ModSec at all tested attack rates. NGINX App Protect also had 4.7 times lower latency than ModSec at that 99th percentile and 1,000 requests per second. And it's roughly the same when we started introducing bad traffic as well. And you could sort of see the latencies of App Protect and ModSec diverging at those higher percentiles. So the higher up we got, the more they diverged. At the 50th, they were pretty comparable. So really, it gets pronounced after about the 95th percentile. If you look at the fully managed offerings, App Protect WAF had 128 times lower than AWS WAF, which is a lot at that 99th percentile. And then it was even more in certain tests, depending on the test that you like at, than Azure. Now again, they're fully managed, Azure and AWS, so we don't know what our underlying compute resources. I can't imagine they would be anything much less than what we were using though. You know, So it is really difficult to get that true apples to apples comparison. I can only get so close in network proximity. But those differences still, I think, are fairly minimal. But once you get to that 90th percentile, you start to see it pronounced. And I think that's really, really important to know. So keep in mind, though, that optimizations on all platforms would be possible if we had internal testing we could do. So I would love to see that, some internal tests. But again, you're a customer just like we are. You can only, when you get these web-based or all cloud-based platforms as a service, that's what you're getting. So it's important to test to see what it would do in your environment. So say, hey, we used it for ours. And it would be really awesome just to see, say you were kind of hybrid cloud and you had some on-prem stuff that you wanted to protect with some of these technologies. It'd be interesting to see what kind of latencies, comparable latencies. And that's why we've provided the GitHub repository. Speaking of which, I want to look at that a little bit closer while we have a little time. Yeah, we're good. So I wanted to go through this a little bit. So if you would like to do your test, again, I've put the link here for the Vegeta tool, GitHub. It's a great tool. I like it. There's another tool out there called WRK2, which actually is kind of cool. It's just like it, but it actually allows you to do some Lua scripting. So if you want to really be creative with your attack patterns, you could do that with that tool. I don't think you can do much scripting with Vegeta unless you like shell script it inside and do some other, fancy dancing around with that. But I think if you want to get real serious and generate some workloads that match maybe the ones you see, you could use WRK2. Or if you really want to get fancy, go to JMeter. Okay, but this still, for just the testing we did, this was plenty fun. Now the different components, again, I'll go through those really quickly. The backend API, again, were those C5N X larges on EC2. We were running Ubuntu. Okay, I couldn't remember if it was CentOS or Ubuntu, but we were running Ubuntu for that. Again, all you have to do, fire one up of those in the cloud. First thing you're going to do is increase the open file limits from whatever the default is, 1024, 2048, I can't remember, 4069, whatever it is. You'll just increase it to 64K. And then you can, and we used open source NGINX as our backend API. And you'll see that there's a script up here that has the configuration in order to return the 1024 random characters. You can use the one we generated, or you can also generate your own using Python if you'd like to create your own string. I've also done this testing with more scripting, like where it would generate random, a different random sequence every time, but I couldn't find any, I didn't determine there's any difference. It didn't make a big difference. So I just went with the same random string. And then just basically after you fix your config, restart, and you should be good to go. On the attack side, this is the Vegeta client. You need the prerequisite for that is Golang. So just make sure you've got Golang installed on your server, and then you can do a go get from GitHub, and it will install. You'll be ready to go. And you can just call it from GoBin or add GoBin to your path, and then you can call Vegeta directly. So then this gives you the script on how you would attack this API directly. So you would obviously put your own internal IP address, not mine, in there. Okay, on the NGINX side, we actually use CentOS for this one. They support, NGINX Plus supports a number of OSs, but we just chose CentOS. We've done that same one in the past, and we just wanted to be consistent, I guess. There's a few other things that you might need to do, and you'll see this if you go to NGINX Plus's documentation. This kind of follows along here. There's a few things that you have to set on the SE Linux side in order to make sure you don't have some issues there. That's probably the number one thing I run into when I install it, is if I've got a SE Linux setting that's different than what I need. On the ModSec side, here's just all the commands. These are just one right after another. Everything from the OWASP CRS that we used, how we installed everything. And then on the App Protect WAF, it's a little simpler just because you can basically install everything with Yum or what is it now? DNF, I can't remember. Anyway, you can do that, and then you can just curl itself and just, and then you can practice with just a basic script injection just to make sure it blocks that. You'll want to make sure you get a request blocked message there. With WAF and Azure, you just basically follow their documented steps. So I just put a link in there to that. Oh, we did use 3.2, looks like. I might have had that in the wrong slide. So if I had that in the slide, I apologize. I think they did have a 3.2 out. Then the test sequences, basically, again, I did some shell scripting with Bash to basically spin through each of the attack rates that I want. You could make this, you could say, you could make this an array of 1,000, 2,000, 3,000, have it, for loop through all that, or you could for loop through your different endpoints. Anything that you want to do there. Again, we did something different on the Azure side because we were using an Azure VM and all that. So really, I highly encourage you, if you're technical minded at all and you really want to see what this would look like yourself, or if you want to spin this up and test it in your own environment, I would highly encourage you to do so. I think it's actually kind of a lot of fun. So hopefully this GitHub repository will give you all the information that you need to be able to do that. So I guess we're to the end of the content that I had to share. I'm going to take a peek here at what questions we might have to see if anyone has asked any. Okay, we've got a few. So I'm gonna go ahead and take one here. One of our attendees asked, which virtual machine types did you use on Azure? That's a good question. I guess I didn't talk about that. We talked about the C5Ns quite a bit, but the only problem on the Azure side, now I will also say this, there's not a great one-to-one VM type on Azure that matches the CF5N family that I can tell. Azure recommends the F series for medium traffic web servers. So I guess that has better network throughput than some of the others. The C5Ns do have a little bit more memory per vCPU than the Azure F series. But honestly, the workload was not super memory intensive. There wasn't a ton of memory pressure at all. In fact, it was mostly CPU pressure. So when we monitored those things during our testing, we didn't feel like memory was a bottleneck. So just because the AWS EC2 instances had a little bit more memory, it didn't seem to impact the outcome at all, as best as we can tell. So that's a good question. Thank you for that. Let's see, what other question? Let me see, we got. The other question was about the GitHub repository. I think I actually addressed all that in there, and I hope you find that repo useful for your own testing. I talked about this other question asked, what are some other load testing tools you would recommend? I think I talked about those two as well. Besides Vegeta, there's WRK2, Work2, which is, I think it's built on another one, so it's like its own. And then of course, JMeter is great if you've got some kind of workflow tests you want to do and you want to build that out. Those can be a lot of fun. Let's see, anything else here? Yeah, that's all the questions I see here. So anyway, that was, if anybody has any other questions, I guess it might be a little late now, but unless I see something else pop up, I just want to again thank you all for attending. Get you out here maybe 10 minutes early. But anyway, thank you. I appreciate you taking the time to listen to this webinar. I hope that you found it useful and helpful and instructive. Again, I encourage you to repeat these tests, especially if you're evaluating security architecture for yourself, and especially in the high performance area. I think load testing is a very good discipline to get into to see how things are affected by the changes you make within your environment. Again, I appreciate the time today. Hope you all have a wonderful rest of your day. And with the upcoming holidays, please be safe, be well. Thank you all so much.